So next up will be Intlvac. Intlvac thin film, it's a vacuum systems and coating company. It dates back actually to 1967, I guess, in its under its current name in 1996, specializing in coatings on, well, our speaker today will be talking about coatings on chalcogenides, silicon, and germanium in the IR range, something that is called the diamond-like carbon films. So we have Dino Deligiannis, the president. He's been working on diamond depositions since 1986. So Dino, please go ahead.
Everyone seeing my screens now?
Yeah, we can see it.
All right. Well, thank you for the introduction. I mean, diamond, you know, it's a strange thing. It's a very dense material, and people have been trying to make it synthetically, I think, ever since someone figured out they could like dip lead coins into gold and make them look like gold. The next thing was like, how do we fake these gems? And I was just mentioning before the start of the meeting, back in 1986, you could have bought an epitaxial diamond reactor and made pure diamond films. In fact, I had a 1 millimeter sheet of diamond, which was great for cutting ice cubes, and it was absolutely perfect. And back then, everyone said, well, you know, you'll never sell it because everyone will be able to tell that it's not natural, because natural has inclusions. Fast forward to today, go and look at synthetic diamonds at your diamond ring guy, and it has all kinds of inclusions and things, and it's virtually indistinguishable from natural material. So making diamond, I think there's lots of ways to make it. I'm going to tell you about the various ways that we've made it here at Intlvac. I have a pretty extensive technical team of PhDs and engineers here, and so at Intlvac, we don't just, our goal has never just been to build machinery. We build things with a process. So we develop thin film coating processes. We develop the machinery around the process. So it's kind of the opposite way that a lot of other things have happened in the world. And so out of that, we've come up with a number of platforms for precision optical coating by plasma enhanced, by reactive magnetron sputtering and ion beam sputtering. Also diamond-like carbon, we've made it by physical vapor deposition, ion beam deposition, and plasma enhanced chemical vapor deposition. We've also been looking at and developing different applications with ion beam. And so there's a big interest in ion beam technology for ion beam figuring and super polishing of surfaces. So those are the areas of technology that we operate in the precision coating area.
Hi, I'm Dino Deligiannis, and this is Intlvac's Thin Film News of the Week. Behind me is one of our diamond-like carbon coating systems that's shipping out tomorrow. It's one of a series of machines that have gone out of this facility this year for putting anti-reflective coatings down on infrared optics. I'm holding an 18.5-inch silicon wafer, which, as you can see, is coated with 1 micron of diamond-like carbon. We can vary the sp3, sp2 bond ratios between diamond and graphite to get the properties that we need that makes this a super tough, scratch-free coating. It's ideal for use on soft infrared materials like silicon, germanium, chalcogenide glasses, zinc selenide, and zinc sulfide. So consider us when you want large pin-free coating areas for your DLC.
So I'll just pause here before I go to the next step. So this machine is actually kind of unique in the marketplace because although we deposit with the substrates sitting down held by gravity, we have virtually no particulates generated during the deposition. And we have extreme uniformity, and we achieve that without rotation, which is also kind of sets us apart from other people in the marketplace. I can't go into the details on how we do that, but suffice to say, it is a unique thing. And We've been very successful with this, and so have our customers. If you went to buy in North America diamond-like carbon-coated infrared optics, very high probability it will come from one of our customers. And we keep one of these machines, by the way, in the lab here for continuous process development, and that's been going on for the last 14 years. So what I'm going to talk about today really is, what is diamond? What is diamond-like carbon? Its molecular structure, what makes it so special. Talk about our coatings, the uniformity, some of the results of our fine-tuning of adjusting sp3, sp2 bond ratios, our testing and applications. So what is diamond-like carbon? Well, so here's a view of, and by the way, carbon is a great molecule. It likes to bond to many things, and graphite, which is that sheet that you see on the left here, loves and is very strongly bonded to itself, but it's not really bonded to layers above and below it. So graphite is a slippery material. It's used for lubrication. It's in your pencil. But now diamond is, and by the way, it's opaque. It absorbs light. Diamond is quite different. Diamond does not slide. It is much more tightly packed. All the electrons are tied up, and there is no light that really comes out of it. Although, if you look at a big chunk of epitaxial diamond, a thick piece, it actually looks kind of dark. And that's not because it's absorbing light. That's because it's reflecting a lot of light that comes, that's incident on it. And so diamond has a high refractive index, and materials that have high refractive indexes, like the infrared materials, like the silicon and germanium, they reflect a lot of light off the first surface. So the diamond, which is clear and not really giving you any color, looks dark because there's not a lot of light in it. Whereas the material that we make, which is the diamond-like carbon, is a sort of mashed up mixture of these two types of types of graphite bonding. And if you're able to adjust the bond ratios, you adjust its property, you adjust its hardness, you adjust its coefficients of friction. Graphite, for example, is electrically conductive along those lattice planes. Diamond is not conductive, pure diamond. I mean, you can dope it to make it conductive. So here at Intlvac, we produce hydrogenated diamond. And so you can see this region in this ternary phase diagram where we operate, and we have a number of process levers that allow us to move around in this light blue shaded area. So what makes diamond so special? I alluded to some of those properties: low coefficient of friction, high abrasion resistance. It's amorphous. It's ideal for infrared optics, as I mentioned. Infrared materials, silicon, germanium, chalcagenide, they have a high index of refraction, which means that they reject a lot of the light that comes off the surface. If we're looking at this lens here that's coated with DLC, I can see the fluorescent light, above it reflecting back, and we're seeing the reflection. So if you lose 40% of the light on first surface reflection, that's a lot of signal that's not going to your detector. And so putting diamond, a single anti-reflective layer of diamond, and the coatings are typically around 1 to 1.1 micron, depending on the wavelength that we want to center it at. We can reduce that first surface reflection and get a lot more into it. And so typically a DLC coating on an infrared lens array, this will be what is pointing out at the environment. This is what's seeing the sand being kicked up, or just sitting there exposed to the elements, hot, cold, and you get some other freebie properties like corrosion resistance. It's biocompatible. Of course it is, because it's carbon. Your body's not going to reject yourself. It can be made thermally conductive. We have ways to make it thermally conductive. Sorry, electrically conductive. It is thermally conductive, and it is hydrophobic. So go back to Intlvac and how we set the bar for DLC. We do that by being able to control the sp2 and sp3 ratio. And so being able to do that while having a very large uniform coating area allows that machine that we're standing in front to pretty much run continuously in production 24/7. It's a very clean, non-contaminating process. And so what is it? What are we doing? Well, we're adjusting that combination of sp2 to sp3, and you can see here in our graph we have these all represent different runs, and as I mentioned, we have a variety of process levers. There is pressure. There's one of the biggest ones is the hydrocarbon gas. There's other gases that we flow in at the same time. There's the bias voltage. But being able to get a handle on those things allows us to adjust this ratio. That ratio, by the way, also corresponds to a specific refractive index. So we can actually not only just adjust the hardness by having a harder material, we can adjust refractive index. And so, as I mentioned, it's actually a very unique internal design. The electrodes, the way we conduct the gases in the system. This allows us to make large pinhole-free coatings. And we have a 20-inch diameter coating area, which is not something that I've seen from other vendors in the marketplace. Our coatings are mil-spec compliant, and you can see they are very repeatable from run to run. Now, we have developed DLC processes on a variety of materials. This one is on gas IR. I'll also show you that, as I mentioned before, we have the ability to adjust that bond ratio, which gives us a different refractive index. And we have actually worked out that these are kind of ideal ratios for these different materials. The one that's we did for a polymer, that was actually for a part of a cell phone camera where we needed to provide slip, reduce stiction onto a plastic part. So we actually designed a deposition process that was able to satisfy that, and then they made hundreds of thousands of parts, and so it's interesting. You can put diamond-like carbon films down onto a lot of things. I'm really primarily talking about optics. You can deposit it on metals. We also found that it also goes down fairly easily on oxides. As I mentioned before, zinc sulfide, zinc selenide. And there's a whole, market basket of chalcogenides. These are kind of soft mixtures that are held together by van der Waals force. And so there are different strategies for protecting those. And the really big interest, I would say, in the last few years has been to replace the silicon and germanium, which are single crystal materials, with things like chalcogenide materials that start off as a marble and then are pressed into the final shape. And now this is the lens, the infrared lens. So they are soft, and one of our I would say probably the last 8 years has been solid development on our side to have our diamond, diamond coatings provide, this protective layer on chalcogenides. So those are the materials. If it's widely adopted into automotive and cell phones, that's what it's going to be made of. We're not going to have germanium lenses, driving around in our car. So what I'd like to stress and impress upon everyone is that we have a really concerted effort on DLC development. We've never stopped really since we really pushed out the PECVD. And I should also mention, before the PECVD, we did have a process we were using by end hall ion source. And we found that was a very dusty process, not as good as what we were able to achieve by PECVD. And so what I didn't mention a lot about was what these process levers are. We have run through the virtual whole gamut of every hydrocarbon gas, either as a gas or from a liquid source, to characterize them, because all of them have different amounts of hydrogen on them. All of them break apart differently in the plasma. And so there are different, gases that we found that are ideal for creating a certain ratio combination. And these are some of the specs that we've been able to comply to. The most popular one, by the way, or the one that everyone asks for, is the sand slurry wiper test. So a very specialized grain size of sand sold by one company in the UK is bought by everyone, and they take a wiper and water, and this coating has to survive some set amount of wipes. I forget how many thousand wipes it has to survive at a certain force. So that basically is what the industry builds to. As far as applications, I mean, we all know about a lot of the applications. I mentioned corrosion resistance. You can see a couple of pictures here. One of them is a camera assembly, IR camera assembly that's on the wall between the US and Mexico. So one of our customers was very fortunate to get a large contract to supply these camera assemblies, and you can see the DLC coating on that large optic. The other one, as I mentioned, the up and coming one, is the application for really consumer electronics. So I bought a small IR camera for my cell phone, or you can run with my iPad, and this is a nice picture of my dog Murphy in the infrared. He's a very happy dog, and he's happy that I'm able to buy him kibbles by selling DLC machines and technology. So that's the offering from Intlvac, a short description of what we do. Please feel free to join us in our breakout room, and we can talk with some more detail. Thank you very much.
Okay, thanks, Dino. By the way, I want to point out that the breakout room will open at the end of the hour. But yes, definitely, please join us in Intlvac's breakout room. I just can't resist saying something. The sand slurry wiper test reminds me of a previous job that we were working on a coating where we had a Scotch tape test, and you use the Scotch tape to try to pull up the coating. And if it doesn't, then you've passed, and if it does, you failed. And I love these sort of very qualitative things.
That was you have to buy a special mil spec Scotch tape to do that with. and by the way, someone sent us their tape, which from China, which had like super adhesive on it, and so that was causing issues because it was ripping everything off. Probably better for making like fullerene tubes or things. But anyway.
So, and by the way, I don't know if I'm coming through here on my audio, but we're going to have to move on, and so there will be questions in the networking session at the end of this hour. So please go to the breakout room for that for more questions.